Hi, everyone. My name is Martin, and I work in the area of partial differential equations, one of which is displayed here. So, first of all, for all of you who don't know partial differential equations, it's like a variety of different differential equations which have like a wide range of applications, like a really huge range of applications. And just to name a few for those who are not enlightened, like I am, of course, it's like, for example, material sciences, astrophysics, climate modeling, or also weather forecasting. So the equation I brought with me here, and I hope you brushed up on your Greek alphabet skills, is the Navier-Stokes equation for fluid dynamics. So in a sense, this describes like the flow of, let's say, water for the moment. All of those different terms here have like different physical interpretation. For example, we have like some external force on the fluid. This is called like the viscosity or stress term. Then here we have like the gradient of the pressure. Obviously, if we deal with fluids, you know, pressure is a thing. Then some of you might know this. It's like the equal sign. Here we're speaking about the self-advection term, and this is like the change of the flow speed and some density. Okay, so let me tell you how someone who I came to work on my project. So my project is not actually solving this equation. It's actually kind of hard. But I'm doing like something a little bit easier, but to understand the way I came to consider my problem, let me tell you the story of how I didn't get my funding. Okay? So I brought along my favorite ball tie. And so everything started with, let's say, a company approaching me and saying something like, hey, we're looking for a mathematician who can solve this equation. So I would go like, okay, so why would I? So, you know, this equation can actually be used for weather forecasting. That's what we really want to do. That's for the good of all humanity and, of course, our business interests. So, well, okay, let me have a look at it. Whoa, that looks horribly complicated, so many terms. But you're a mathematician. You have been studying mathematics and equations like this for years. You surely know what to do, don't you? Like, if you can solve this, we will obviously also fund your research and everything. Okay, in that case, oops. The equal sign got missing. So, in that case, let me actually have a look at this. Okay, so I think I can do something with it, but bear with me for 1 second, okay? So, you know, it's very complicated. Let's make it easier for the moment, okay? Just for now, okay? Forget the external force, okay? Let's just forget about it. So, you see, it's still quite complicated. And, you know, personally, you know, I never really understood nonlinearities. So, for me, that's just not an option dealing with those kind of things. So, you know, standing on the stage is enough pressure. So, I don't really want to deal with pressure. And also, there's this thing that I don't know whether my audience actually knows Greek letters so well. So I want to just replace them. Like this becomes a 1. And, you know, instead of having this term, you know, we put up this term. It's essentially the same, but written in a different way. So yeah, this then becomes the equation that I'm considering. Well, okay. Let me put it like this. So you're saying that. So you want to tell me that solving this equation actually gives you the same solution than solving the original problem? I mean, don't be ridiculous. Of course not. It's completely different. I mean, can't you see? Like, so yeah, well, at that point, I could not guarantee or secure my industrial funding, unfortunately, but Yeah, I don't know why, really. So, yeah, looking at this equation. So this is the equation I'm actually considering in my PhD thesis. I mean, it's quite an easy equation. We all know that it's the heat equation from kindergarten. You know, I don't need to tell you. I don't need to tell you a lot about it, really. But let me tell you why it is actually important or useful to consider this equation. I mean, some of you might think now that, you know, okay, this has nothing to do with the original problem, so it's kind of useless. It's kind of artificial, and you wouldn't be wrong. But let me open up an analogy. So it's like this equation is like a wheel. The original problem that is like on the ground here somewhere is like a car. And what we really want to do, or what we really want to have, is like this perfect weather forecasting, which is like the car. But can we build a car without a wheel? Probably not. So the wheel itself might be useless, but then we can apply it, like understanding and solving this might in some sense be necessary to then solve the real problem, to then build the car, and then humans will actually appreciate what we've done here. So my message overall should be that no matter how absurd those formulae look, they have an application, though not everyone might see it on first sight. Thank you very much.